So last time I explained about this smooth mean curvature vector and also some of the basic properties. And today, okay, just skip a few things. Give an indication of how to construct this approximate curvature flow. And also give some indication about how to, in the end, indicate what you need to prove, okay, in the last step. So what I did last time was for each, for J fixed, this is integer. So you have, and also you're given this initial data, which is this n pair of open set, mutually disjoint open set. Open set. And so this complement is your initial data. Basically, this is the initial data of the mean curvature. Let's see. Yeah, it's really essentially this guy. But you can also think this n plus 1 minus E0i. Okay, and also the assumption was, well, this guy is a rectifiable set, and the n-dimensional measure of this set is finite. Okay? So that's, and also rectifiable. Okay. Okay, so these are given initial data. And as I said last time, so what you do, so I'll just do the one step only, and the rest is just repetition. So what you do is you're given this, then first you do this Lipschitz map, which I'll explain this today. Lipschitz deformation. And you get this intermediate set, which I indicate by this hat. This is not a Fourier transform. I think it's just notation. E hat n of delta t. Okay, and after this, you move by this smoothed mean curvature. Okay, and you get the next the set for the next time, delta t. Okay, okay, so that's a scheme. And well, basically, I explained the tool that you need to do this part 2 days ago. And yeah, so let's see. Let's see. So let me write this way. So maybe I introduce this notation delta gamma to be just this sum of E hat I of delta t, and this will be, again, I'll explain this, but this will be a rectifiable set with finite measure. Okay, so and let's see, and also I guess the gamma delta is the again 1 to n of boundary of E I delta t. Okay, so all right, let's see. So today I fix epsilon already at this point. Let epsilon to be 1 over j to the actually maybe something like 8 is good enough. Okay, and now this time step size delta t, I take it to be much smaller than epsilon to the 4th, which will be I'll explain why this is the case. Okay. Now so okay, assume that you did this Lipschitz deformation part where you get the rectifiable set with finite measure. Okay, so I'll explain this part later. So assume that this is already, we know that what this is, rectifiable set and finite measure. Okay, so now we can then define this approximate mean curvature vector with respect to this guy. Okay, so this one. For this one, I compute the approximate mean curvature. Okay, as last time, and so. This is the one that we defined last time, this approximate mean curvature vector. And I use this to move the surface. Okay, so well, actually more like, it's not really surface, but it's more like a domains that you move. So let f of x to be, is a map x plus delta t times this h of epsilon gamma hat delta t of x. Okay, so that's the map. So f is a map from Rn plus 1 to Rn plus 1. Okay, and let's see. So by lemma 2 that we had before, by lemma 2, we know that the C1 norm of this H, okay, H of epsilon gamma hat, C1 norm of this is of the order of, this was like C to N, and let's see, roughly, okay, maybe I just roughly says, this is of the order of 1 over epsilon square, okay? And also, yeah, okay, maybe that's good enough. And also, yeah, I should note that this norm also depends on the measure of this set. Okay, so note that this measure of this set is also dependent on this constant here. If you look at the lemma 2, but since we are actually looking at the motion which reduces the measure. Basically, mean curvature sort of reduce the measure. This is bounded. Okay, so that's the dependence on this constant on the measure doesn't matter so much. Okay, so what I'm saying is this is decreasing in time basically. We'll see this later. Okay, so this I haven't really proved this, but decreasing. So it's bounded. Yeah, remember this, when you compute this guy, the dependence was only epsilon and also the total measure, okay? So, okay, so that's, if this constant blows up, then we're in trouble, but that's not the case. I mean, this guy is bounded, okay? So, we know that the C1 norm is of the order of 1 over epsilon to the 4th, and if we choose this delta t to be much smaller than epsilon to the 4th, then the C1 norm or the, you see this part becomes very, very small, okay, in C1. Okay, so this part, if delta t is chosen so that this is much smaller than to the epsilon 4th. In fact, later we'll choose this delta t to be epsilon to whatever, it's like 3n plus 20 or something. Okay, so it's much smaller than epsilon to the 4th. So this delta t is much smaller than this. So meaning this part, okay, so is very small in C1. Okay, so that means this map is actually diffeomorphism because you have the identity part and then very tiny C1 map here. Okay, so that's actually diffeomorphism. So this F is diffeom. Okay. As long as this delta t is small enough. Okay, so that's one that we use. So we map this E hat 1 delta t En at delta t by F. Okay? and let basically the image EI of delta t to be just f of this EI hat of delta t. Okay. So remember these guys, I didn't say this very clearly, but this actually is also partitions of Rn plus 1. Okay, so it look really like the initial data. And then you map this by this diffeomorphism. So I haven't explained this part yet, so may not be so clear, but this will be this will be partition. Okay. And by the way, these guys are also open set. So this is open set. Okay. And also let's see. So the boundary of these sets will be basically the boundary of these sets too, because it's a diffeomorphism. So f of this boundary, this one, boundary of this will be just a boundary of this, the union of, well, I guess maybe I wrote this here, so maybe I just use this notation, delta t. Okay, so since it's a diffeomorphism, just open set goes to open set, boundary goes to boundary set. Okay, no problem with that. Okay. Yeah, and okay, so this is this step of the smoothing curvature. Okay, so I have a few lemmas here. Next, so lemma 4 is for simplicity, let me write this gamma to be this intermediate set. Just since I don't want to write this every time, let this here gamma refers to this intermediate, okay, boundary, and so that means under the map F, this gets mapped to basically the next step guy, this guy, okay, delta E, okay. So then we have the following estimate. That is the n-dimensional measure of this f of gamma, which is what I just said, this one, minus hn of gamma, and minus delta t, and divergence of tx gamma, h of epsilon gamma, dhn. This is bounded by a constant which only depends on n, and the delta t square times the measure of gamma, okay, times, sorry, another one, the first derivative of h gamma. This is infinity of square. Okay, so we have this estimate. So so this is telling you up to quadratic error with respect to this time grid size. So this is square. It's very important that you have square. The difference of the measure. Now you have this subtraction here. So what this is saying is that the change of this area is basically equal to this plus some quadratic error, okay, if you do this map. And this is actually very easy. By the way, I should put the number 19 because it refers to this later. So a proof is just an area formula, very easy. And after all, this is a diffeomorphism, so all the classical stuff works here. So just the area formula tells you that this area should be given by So this is area formula. Is given by gamma of the Jacobian of but you restrict this to goes to tangent space of nabla f. Okay, that is, you compute the gradient of this, but you compute the Jacobian restricted to the tangent space of the. Okay, so that's the usual area formula. And the nabla of f here is as you can see very easily. I mean, this is just derivative of this. So x part, of course, is identity map, identity, and plus delta t, and then the gradient of first derivative of h. That's the nabla of f here. And the Jacobian of this, I think most of you must be familiar that if you compute the Jacobian of this, the one that comes out, since you have identity, the first term is 1, and the second term is a trace of this restricted to the tangent space, and the next order term is a quadratic term. Okay, so this, since we have that, we can continue to have this is equal to gamma of basically 1 plus delta t, and so trace of this restricted to the tangent space would be just a divergence, actually. So that this would be divergence of the tangent space of nabla h. Oh no, sorry, h. Yeah, you're taking already derivative. So here, and a plus order of delta t square times this derivative term. Okay, square. So basically, that's it. Because this is just the first term is just the measure of gamma, and the second term is delta t, and exactly divergence of tx gamma f h, which is what we had here. And the last term is some constant times basically delta t square, and then you have this L infinity square times hn of gamma. Okay, so that's all. Okay, so that's, let's see, I guess it's fair enough, right? This, if you subtract the right hand side, these two terms from both sides, and that's what you get, okay? No problem, I hope. Okay, so next, okay, so it's good, we've seen something like this before. Last time we computed what this is exactly, I mean, with even equality. But okay, at the end, the estimate that we want is actually not in terms of this intermediate object that is this gamma hat. Gamma hat, I don't want this at the end. Actually, I want to describe everything in terms of gamma 0 or gamma delta t and so forth. Okay, so because this is intermediate object, which we don't really want to keep track of after all. Okay, so I don't want this, for example, here, this is with respect to, well, actually, this is tx of gamma hat of delta t and so forth here also. Okay, maybe I should write like this. So this is this intermediate guy. So I want to replace it by the object which we want to keep track of. So because of that reason, I give you this next lemma. This tells you that you can actually look at the difference between these two objects, that is tx of f of gamma and h of epsilon of, here's f of gamma instead of gamma. Okay, this difference Tx of h of epsilon gamma. If this difference can be bounded by delta t times epsilon to some number here. I actually, when you compute, it's in my paper, but it's not so important, but some epsilon to the some power. Okay, so you have to estimate this, but here's equation 20. So I don't want to go the computation in detail, but I just want to say that you see the point here is that in some sense the size fx minus x is the size is delta t to something like epsilon to the minus fourth, okay, at most, in terms of order. Okay, so you can actually think, well, this difference between these two of this order, delta t times some epsilon to the negative power, so it's actually very small, and you can estimate using basically this delta t times some epsilon to some big negative exponent. Okay, so this is something that you have to see how it goes. You use the exact things you use, I sort of forgot, but yeah. So this is, if you're interested, it's in my paper, so you can take a look up. But the point is, it is bounded by this delta t times some big number, okay? But you see, what you want to do is you want to replace this by, basically by this. Okay? That is, this guy is here. So I want to replace this by this, and but you still have this delta t here, okay? So if you replace it, you do have this delta t, and if this replacement error is of the order of delta t, it's still okay because you have delta t square. Okay? Delta t square times some big number like this can be made controllable by choosing delta t sufficiently small, okay? Because you have quadratic, that's very important. If it's linear, it doesn't work. But since it's quadratic, you can make this term small, okay? So that's the idea. So the key point is really the fact that you have this guy, and then the places where you replace has this delta t also. Okay, so that's why you can do this. Okay, so maybe just I just put go. Okay, I don't go into this. So the next lemma 6 is really follows from the what we did so far. I think let's see. I think I erased, or I didn't have it, I guess. Yeah. So it's okay, by combining 17, which we had last time, 19 and 20, we can immediately get the following. So we have Hn of f of gamma, which we call it as basically gamma of delta t, the next step surface, plus delta t, and here's Rn plus 1, and H tilde epsilon of f of gamma square, and d mu epsilon gamma, f gamma, and let's see, is less than equal to, here's Hn of gamma plus delta t square times Cn h gamma, and let's see, here's should be square delta h square, yeah, plus epsilon to the minus 3n minus 18. Okay, so that's 21. Yeah, so this follows fairly immediately because, yeah, so here we have this, Okay, we have this guy. Now you replace this using this lemma. Okay, so you can replace this by this. And we know by the formula that we had last time, this can be explicit. This is exactly equal to this with minus sign, I guess. Yeah. Okay, so that we saw this, just by follow from definition, more or less. Yeah. So, but now you have the error that is one error is this one, which I took into account here, and the other one is this one. Okay. But note that here is delta square because you have delta t in front of the integral. So, okay. So I hope this was clear. Now at this point, I choose delta t finally to be, let's choose this time step size to be something epsilon to the 3n plus 20. Okay, so that this term become less than, okay, for sufficiently small epsilon, become less than epsilon squared times delta t. Okay. So this error term become less than epsilon squared times delta t. Okay, so this is a part about Lipschitz deformation. And actually, this was for just an entire measure, but actually what you have to do is here, I don't do it, but also you need to look at also for any phi in script aj, one needs to look at f gamma of phi the hn minus I of gamma of hn. You need to decimate this one. You see, we just here what's written is the special case when phi is equal to 1. Okay, phi equal to 1 case, we did it. Okay, but in general, you have to do this also because Brakke's inequality is precisely described by this type of inequality. Okay, so you have to do this kind of things. But we have all the tool actually already because you do the area formula again, and then what you end up having is, in fact, instead of this, we would have well extra derivative term, but also the one which has phi here inside. But this is exactly we had last time, right? Like with some error estimate. So you can do exactly you can kind of see how that goes for the rest. Okay, so you need to do this, but also another things you need to do is also the volume change also. So this is related to BV formulation. Okay, so you need also UI of delta t phi. Well, this phi is actually not the same phi. Any C1 function actually. C1 compact maybe. Also, what you can do is you can actually also estimate this type of quantity. Okay. This is something you can do also using the formula, this formula, in fact, for the formula of f. So these things you can do, and but I don't. So I'll skip this part, of course. Okay, so next. So I keep telling about this smooth mean curvature vector. Now you may wonder that maybe you can just keep doing only this, smooth mean curvature motion. That is, you're given this initial data. You compute the smooth mean curvature vector for that, and then just move. You can repeat this, okay? But actually, there's a problem of doing that because the reason that we need to have this this Lipschitz deformation is there are two reasons. And one is that if you don't have this Lipschitz deformation part, then not that, as you saw, this is just a diffeomorphism. So if you don't have this Lipschitz deformation part, you'll be just doing a smooth deformation repeatedly, okay? Only deformation. And okay, that's, okay, maybe it's good. There's a question, maybe that's good, but obviously you see there's no topological change occurring, okay? And for the grain boundary motion, typically you do have some topological change. Okay? Something may vanish, some triple junction may collide and so forth. And that kind of thing is not going to be described. So, so the problem is that so you will be only all diffeom, which you don't want. Okay, so you do want to have a topological change naturally. And the second thing is also important in that after all, this mean curvature is obtained by doing a smoothing. Okay? At least you introduce this length scale of epsilon. I mean, epsilon is small, but epsilon is there still. So you basically don't have any kind of information smaller than epsilon in terms of length scale because you're diffusing. You're sort of smearing out the detail, right, by doing this Gaussian. So in some sense, you lose the control of the length scale smaller than epsilon. But when you take a limit, okay, I don't do that part in this lecture, but at the end, you want to take a limit. But now you have some problem. Epsilon goes to 0, yes, but you want to know also what's happening in this small scale. Okay? So to have the information smaller, so to gain some control of measure in the order smaller than epsilon. Actually, what you do is this Lipschitz deformation is not just doing a Lipschitz deformation with no purpose, but what this does is that actually it does do some kind of local area minimizing. Okay, it's not quite minimizing. We will see this, but local mass minimizing sort of things, mass minimizing or well, this is not quite right, so maybe I should just put quotation. Yeah, in some sense, I choose this Lipschitz deformation so that it does do some kind of regularizing. You really see that effect in the end. Okay, so that to explain this, it's a bit more. It's a little bit complicated, but I hope that's really fairly clear. So let me introduce a few notation first. First, even though I want to do Lipschitz deformation, I can't do any arbitrary Lipschitz deformation. I need to somehow preserve the structure of this partition-like, structure. Okay, so to do that, I need to introduce some kind of admissible class. So if you're given partition, so this is, forget about what we've been doing so far. This is called I say open partition of an element if there are a couple, three conditions, E1, En are open and mutually disjoint. And some of them can be open, some of them can be empty set, okay? Some can be so they are open set, and some of them can be empty. And the complement has a finite measure. Okay, has a finite. Of course, complement is a closed set and has a n-dimensional measure finite. Okay, so in particular, this set cannot have interior points, because interior points this would be fine. This can't be finite. So this implies, in particular, that Rn plus 1 minus this set is just a union of those boundary, because there is no interior point. And finally, C is that condition C is that this boundary set, this is rectifiable. Okay, so now, yeah, this is, okay, as you know, you may know that finite measure doesn't mean that it's rectifiable. So there might be a so-called purely unrectifiable part, but I assume that that part is not there. Okay. And okay, so and if it's open partition, then we say, let me write this, right? This M. So M, I always think this M to be, yeah, this way. Okay, so it's an n tuple of sets, open sets. Okay, so I say M is open partition of n element. Okay, so that's just a notation for this type of things. And as a notation, just for simplicity, when I write boundary of M, this is just a notation for just a sum of the boundary of this EI. Okay, so it's just a notation. For, you know, writing this every time is a bit tiring. So let me write this way. And so that means if I, okay, so this is like a variable notation, but if I write this, that's Hn of this M, which is Hn of n of EI. Okay, so just this is again just a notation. Okay, for and note that our assumption on the initial data is precisely that initial data belongs to this class. Okay, note that our initial data belongs to this M. No. Open partition of n element. Okay. And so that's a kind of class of sets that we want to just kind of keep moving. Okay, and it's actually okay. So this is a class I thought about. I mean, it wasn't written anywhere, so I spent some time. What would be the right class to think of? And this seems to be the right one. Okay, so the next definition is that. Yeah, this is another definition. So let's, given this open partition, and a Lipschitz map, is called, with respect to this open partition, M admissible. Okay, so if the following is true, okay. So so this is depending on your partition, okay. Given a partition, I define this admissible class for Lipschitz map, and it's defined as follows. So first you define EI tilde to be the interior point of the image of this EI. Okay. So I define, okay, so F is a Lipschitz map from Rn plus Rn. So you map this EI by F, and I just take interior points of this image. I will give you the example of this later, but just for now, I just go through the definition. Then I ask, so this is a requirement. Then E1 tilde, En tilde are disjoint. Okay, and also B, the complement of this image is included in the image of the boundary. So these are the requirements. Okay, so I say it's called M admissible. Lipschitz map is called admissible if you define first the interior points. I ask them to be disjoint, and also basically the boundary. Boundary of. Okay, sorry, it's not boundary, but this minus this open set is included in the image of the boundary. Okay. So this may be a little bit strange. But before I give you the example, I just tell you just an easy lemma. Lemma 7 is that this newly defined this E1 to En tilde is again open partition of n element. Okay. I just give you this, and then I'll give you the example. But it's very easy because, okay, for this to be open partitions, one needs to check is just these three conditions, right? And proof is very easy. A is, well, A is obvious because I'm taking interior points, so it's open set by definition. You know, EI tilde are just interior points, so it's open set. Okay. And also, I'm requiring them to be mutually I would say mutually disjoint, yeah, like disjoint. Yeah, I think you understand, but mutually. So they are disjoint by definition or requirement. So they're fine, and so A is fine, of course. A is okay, and the B is also okay because the n-dimensional measure of this complement this is included in the image of the Lipschitz map of this one, okay, by this second property. Okay, that's also a requirement. It has to be included in the image of the boundary. And of course, as you probably know, the Lipschitz map has this property that house of dimension, a measure of the set increases only by the factor of Lipschitz constant times to the n. Right? And this is by definition is bounded, so it's actually bounded. Okay, so that's fine. So this condition B is satisfied easily. And the last condition is also satisfied because, it is well known that counter and rectifiable set, if you map is, the Lipschitz map of counter and rectifiable set is counter and rectifiable. If F is Lipschitz, and this is a property. If you know the definition of the counter and rectifiable set, this really follows from the definition quite easily. Okay. And any subset of counter and rectifiable set is also counter and rectifiable by definition. So that means this set has to be also counter and rectifiable. Any subset is also counter and rectifiable. So, okay. So this means that under this admissible Lipschitz map, you map this open partition to open partition. Okay, so that's good because you can preserve this property. Okay, so now the kind of things you want to do with this admissible map is the following. For example, it is often the case that so this is very easy one. So suppose you have like this kind of configuration. Okay, so diffeomorphism cannot do much with this configuration. You cannot reduce the length, okay, by this. But okay, typically you would like to change this. Okay, if you have this sort of grain boundary motions, and if you have something like this, then you typically want to go to this kind of two triple junction, okay, like this. Okay, this has length less than this cross. Okay, and this kind of changes is depending on the problem, I think in some way, but for the sort of grain boundary motion, this would be the desirable topological change that you want to happen. Okay, so for this to happen, actually, what you can do is you do have a Lipschitz map. This which maps is it's a little bit hard to draw this, but I suppose I think the way I think of is let's see, how does it work? You have to come up with some sort of suitable map, but somehow I think let's see, how does this go? I think something like this. You kind of okay. I think maybe. Well, let's see. I think maybe something like this. Yeah. So the things you can try to do is by Lipschitz map. I think this red region you crush to this red guy. This part onto this line. Okay. Onto this line, really. And then you stretch this upper part over to the rest, basically. So you stretch, for example, this part all the way to this part. So linearly, sort of, you can actually spread this part over up to this way, okay? Which you can do it by Lipschitz map. That is, this part remains here, but this part goes to here, basically. Okay, so you can kind of stretch this part so that it will be mapped onto this set. Yeah, And then this part is also basically you stretch it so that this part gets mapped to here. Okay, so this yellow part so basically covers this region. So that can be done. Okay. And actually, this map. Okay, you do this for each part. Like there are 4 parts here. So for each of that, here also and here, and so you kind of stretch this yellow lines up onto this line, and the whole area here gets crushed onto this line. Okay, that's a kind of map. And this map actually is satisfying all these assumptions. That is, you see the image of E1 in this case. Okay, just think about the image of this E1. Image of E1 is include, of course, this yellow part and covers. You see, since this yellow line get mapped to here, the E1 tilde will become this part basically. Similarly here too, if you think about it, because the you see this yellow this part gets mapped onto this one, so it will be this part will be the interior of the image of this yellow part. Okay, so at the end, E1, for example, this E1 tilde will be this part. And the boundary of E1 tilde will be this part, for example, and this part is actually will be part of the image of the boundary of E1 because this white line gets mapped to this yellow line, right? Because this whole region is crushed into this one, so this white line gets mapped to this yellow line too. Okay? So actually, this E1 tilde's boundary is included in this image of the boundary. So this can be done with this map. So under this admissible class, you can actually map this cross into, as I said, something which look like this. Okay. There's F which map this things like this, and the other. Okay, so this is actually is very useful to at the end, and the other kind is the following. So the sort of things you want to avoid, and you may want to do something about is this kind of situation, where here let's assume this is E1 and the rest is E2. Okay, so initially suppose you have this. Okay, suppose you have this kind of picture. And then let's see. So in this type of geometric analysis, the things you want to sort of eliminate is this very thin, long tentacle. Okay, that's your enemy usually for this type of problem. And so you want to eliminate this. But now what you can do is, okay, so you take a circle. In this case, maybe circle is good enough, and you can do the following. So you can take a little circle here, and then you map this circle to this entire ball. And the rest is just identity. Okay, so what I'm doing is I expand this ball to this ball. Okay? And then all this part is mapped onto this circle. Okay? So this intermediate annular region is mapped onto this circle. And that's a Lipschitz map. It's a retraction map. And its Lipschitz constant is sort of bounded. It will be big here, but at least bounded. And if you think about what is the E1 tilde and E2 tilde in this case, you see image of this E2 is going to be this entire circle actually, because this part gets mapped to here. So in this case, what you have is that And also, it actually satisfies this admissibility condition because, yeah, okay, so if you think about the interior point of the image of E2, it will be, in fact, this part actually. That's going to be E2 tilde, okay? And the E1 tilde is this part, okay? Because think about this, there is any point here will be the image of any point in here, right? I mean, any point in the circle is going to be, there is some point here that gets mapped to here, okay? Because it's just expanding here, okay? So the endpoint, and also note that the this part is going to be the boundary of E1 tilde, but this portion, there is a map, there's some points which comes from this part, because, yeah, so for example, this point gets mapped to here, for example, so forth. So this little piece of line will be in the image of the boundary. Okay, I hope that's, from the picture, I hope it's clear. What I'm saying is this little line, you have some point that on this boundary that gets mapped to here. Okay, so this condition is also satisfied. Okay. So and in the end, you end up having some picture which looks like this. Okay, so this is E1 tilde and E2 tilde. So you can eliminate this type of tentacle, for example, which yes? Yeah. Yeah, in the proof, what you prove is that, okay, yes. For example, I can use this type of map to eliminate this type of four edges singularity, for example, in 1D case. Yeah, you can do that type of things. And also, this type of map is also used to get some sort of lower bound of the energy or the surface area. Actually, yeah, this retraction map is very useful in the end. So yeah, there are a couple of ways to, actually, I think this is very typical, and this is also very typical. Yeah, this is 1D use mostly up to this point, but yeah. Yeah. So the idea is well, right. Yeah. I think if you're given some singularity, whether you can reduce the area by this Lipschitz map is not entirely clear, I suppose. Yeah. But given something which looks like this, then I can reduce the measure. Sort of. Yeah. Thanks. Okay. So I hope that's somehow slightly convincing. And now, okay. So there's still more definition, unfortunately. Okay. So I hope that it will be reasonably over. Now, so I defined this admissible class. Now, I want to further restrict my class as follows. So if you're given this open partition, open partition, we let the f of this f of mj to be a set of all m admissible set, admissible map, f such that the following is true. That is, there's three conditions. One is that supremum of x, fx minus x is less than equal to 1 over j square. So this Lipschitz map, I'm defining this class of admissible functions, but this does move only a little bit. Okay, so the image changes only a little bit. And the B is that for any phi which is in script j, we have this integral reducing property. Okay, phi of the by the way, I think I forgot to say that I defined, okay, so under this map, I created this new partition, but let me call this as F star of M. Okay, so that's just a notation for this this new partition. Okay, so let me call this as the one that you created by using this admissible Lipschitz map. So so this is the one that I just created is less than phi of the M. Okay, so this holds. So if you put any this script aj function, test function, then this integral has to decrease. Okay, I hope that's clear. Yeah. So this is with respect to new partition, surface measure, okay, and the previous ones. And maybe C. I lost the space, but let's see. Maybe I'll just add here. C is that we have also the following. That is, okay, so E1 tilde to En tilde is this newly defined one. Okay. Then we have also we have to make sure that the change of the Lebesgue measure, okay, so for each I is small compared to the reduction of the measure, okay, of minus Hn of sorry. So for I from 1 to n. Okay, sorry, I think it's pretty kind of complicated, but the first condition tells you that this Lipschitz map is allowed to be only small change, okay, particularly less than 1 over j square. Okay, so so I'm introducing this size here. And the second one is significant in the sense that you put in any test function, basically, script aj, and remember that script aj is the one that, you know, if you look at the scale of 1 over j, this function behaves more or less like constant. Okay, so phi is like really constant, like in a small scale. And note that this changes is much smaller. Okay, so you're really allowed to change a little bit. And this is saying, oh, by the way, in particular, yeah, I forgot to say that, but this admissible class is always include identity map for sure, identity map of Rn plus 1. Okay, by the way, because identity map does everything, of course. Identity map has no problem satisfying this. So identity map is here. So in particular, this is telling you that, I'm sorry, yeah, I think identity map is inside. So, I'm sorry, what I want to say was, no, I'm sorry. Yeah, identity map is in here, but also I want to say was, phi equal to 1 is always in this class, okay? So in particular, this is what this is requiring is that this Lipschitz map has to reduce some measure, okay? Because when phi is equal to 1, this is asking you that the measure has to decrease, okay, at least. But not only constant, but I'm requiring for any function in this class. This is true. And the third one is basically is saying that unless you reduce the measure, you are not moving, this open partition. So this is actually telling you that this domain area changes little relative to the reduction of the measure in some sense. Okay. So, but by the way, this turned out to be a crucial property when we proved the property of BV function. Actually, this was, but anyways, it's a bit technical point. But okay. So now what this is this AB. Well, okay, C is less important perhaps, but this condition B gives a very restrictive. This one is very restrictive in the sense that if the boundary, okay, if gamma, which is boundary, is actually smooth, then this condition actually results in the following, that f of m j is actually composed of only on the identity map if j is large enough. Okay, because this is non-trivial only when you have singularity in some sense. Okay, so if it's smooth surface, if it's smooth, then actually what you can do is you can always cook up some phi such that this condition B is violated. Actually, it's for example, you can think of it's a good example exercise. But if you think about the circle, for example. Now, if you have a circle, okay, you move this circle, okay, basically you want to reduce the length. So in this case, you kind of look at the map that shrinks the map a little bit. But now you can actually cook up some phi such that it becomes positive, away from the circle inside. And actually you can cook up so that the B is violated, okay? So this class of admissible functions is non-trivial when you have something like this. Actually, that's only this is the kind of typical picture where you can reduce the length locally drastically. Then this class is going to be non-trivial. Actually, okay. So it's actually a very interesting way of restricting the Lipschitz map. Yeah, so it does require some thinking for a while, in fact, to get the feeling of this. But okay, so yeah, it does require lots of definition. So this Lipschitz map does a sort of a minimizing in a very small scale, but not only around the singularity, actually. So that's very important because you don't want to mess with a smooth part with this Lipschitz map. You really want to do it only at the singularity. So. Yeah, so by the way, so if your initial data is smooth, then this Lipschitz map doesn't do anything. Actually, it stays the identity map. until some singularity occurs. So that's probably a good way to think of. Okay, I haven't finished the definition of this map yet. Sure. Okay. Yeah, with all these definition defined, yeah, a bit more, just another last maybe definition is that for, if you're given this M, open partition, then define the following number. So okay, so this is, I'm using this Brakke notation. Here's this notation. So I just actually use it also. So delta J of this measure, so it's not Laplacian, it's an infimum of all the Lipschitz, this class Fmj. So now I define this class of Lipschitz map and look at all the Lipschitz guy is, so this M minus Hn of boundary, okay? I define this number. So this is what this is saying is that this is the amount that you can reduce by this Lipschitz map, okay? So that's infimum. So this is the amount that how much you can reduce by Lipschitz map. And note that this f of mj always has a identity map. Okay, so this always has an identity map. So identity map is, of course, gives you 0. So that means this delta j of this number is always less than or equal to 0. Okay. So as I said, whenever you have some singularity where you can reduce the length measure, this becomes a negative number, but otherwise it's 0. Okay. Fine. Okay. So finally, after proving this, you see, I haven't defined what is the Lipschitz conversion is for given an initial data, but here is the answer. for given this initial data, okay, choose this Lipschitz map, let's say G, well, okay, G, let's say G. Sorry. Such that you do some minimizing, or not really minimizing, but at least you reduce the measure, okay? Minus Hn of m. You know, this is really, you know, your initial data, gamma 0. And this is, well, this is, okay, well, that's is less than equal to, well, this number doesn't matter so much actually, but it's actually, okay, I choose it following, actually, this is again the choice of Brakke, which I don't quite understand, but I just follow his notation, maybe. Okay. Here's 22. And let this E1 hat, En hat, which I defined at the beginning, to be this G star of M. Okay. And I had this notation, delta hat is equal to boundary of E hat I. Okay. So that's a choice. Okay. Yes. Exactly. Yeah. So you see, this is a, you know, class. This is just a Lipschitz map, and you know, we don't have any, for example, like there's no condition about the Lipschitz constant, for example, nothing. You know, it's just you're saying Lipschitz map with this class, and yeah. So you don't. It's actually probably not. You cannot find the minimum for this guy, okay, because there's no control really. Yeah. So, but at least you have something, and so I just choose something which, you know, is close. But actually, it turned out it's kind of strange. This part I don't quite understand very well at this point. But this number doesn't matter actually. It could be actually 1/2, for example, if you like. Yeah, it turned out that all the analysis I have in my paper works as well. Actually, surprisingly, this even works even if you have small number here, like this. So this part is a bit strange, but as long as you have some fraction of this to be realized, then that's fine. So this part stays as a mystery to me still. So maybe there's some way you can look at it. But anyway, so I somehow the bracket choose this number. So I just choose it, but it doesn't matter so much. Yeah, it could be like 1/2. But I hope it makes sense to you. What I'm doing is, you know, when this is negative, when this number is negative, then I at least choose something which sort of reduces the measure, okay? Some fraction at least. As I said, 1/2 is fine as well, okay? Okay, so that's the choice that you make for Lipschitz map. Okay, so this at least gives you, you know, like this first step where you start with initial data and then you do Lipschitz deformation. And then after that, you compute the smooth mean curvature vector and then move it. And so that these two steps is the one you do to get this delta. Okay, the next step on. Okay, so yeah, so yeah, that's fine. Okay, so up to this point, yeah, this is 22. So if you combine this 21 and 22, we obtain the energy estimate of sort. That is Hn of delta. Yeah, by the way, so, in particular, as I said, this map is area reducing. Okay, so it reduces the area. But actually, it reduces not only area, but with respect to any test function too. You see, you see it already, but we had this second condition that if you integrate with respect to phi is in this script aj, if you put in there integrate, then you are also reducing the integral value. Okay, so with respect, if you think about the Brakke flow, actually that's good enough because all you want is for Brakke's inequality is reduce the integral. Okay? So so that's okay. So maybe that's as a remark. But so as a result, you get this nice inequality. And here's minus of 1 over minus j minus 5 delta j. It's gamma 0, actually. 0 is less than or equal to Hn of gamma 0 plus epsilon squared delta t. So that's one can obtain. Okay, so note that before we had the, here is, I think, we had hat. Okay, we had hat version before. But now hat is using this. You see, let's see, yeah, here's a hat. Just a moment, let's see. Yeah, it's always a bit confusing because it goes the other way around. Yeah, so you see this formula, if you write this, well, yeah, let's see. Yeah, so this formula tells you that, you see, at the end, this guy is the gamma of delta. Okay. Sorry, this one. So, and this one is gamma hat of delta. Sorry, no, that's not right. Yeah, this is gamma 0. And yeah, so this is gamma hat. Yeah, so that's right. After Lipschitz definition, you get this one. Yeah, so you get this one. So you have this bounded by the initial measure plus this one. But this is negative number, so you put on the left-hand side, so you end up having this. Yeah, note that this is negative. This is number is less than or equal to 0. So it's this with a minus sign, it's plus number. Okay. So that's the formula. Okay, so this is just for one step, and then you repeat this, basically. This is just one step, but you repeat it. And so by doing addition, so then for any T1 to be k times delta t, and T2 to be another k2 delta t, we have by adding. And also, you define this discrete surface guy piecewise constant way. Then you can actually defining gamma delta gamma t appropriately. That is piecewise constant. Okay, so you can, by just adding this and expressing everything more like integral, then you end up having basically T2 plus, basically this part become like an integral, T1 to T2 dt, and H tilde epsilon gamma t square and minus delta t divided by 1 minus j to the minus 5, t1 to t2. And this again, also you define this as a sort of piecewise constant function, dt, okay? No, is less than or equal to the initial, or gamma of t1 plus epsilon square t2 minus t1. Okay, so just by adding this from one by one, you can obtain this this expression. Yeah, I hope that's not too bad. Yeah. Okay. Which I say 24. So that's the so the energy estimate satisfied by this discrete, piecewise discrete approximate solution. And okay, so this is for the energy, but also one can do the same things. One can obtain a localized version that is for phi in script j. We can really, get the analogous expression of t1. So the idea is very similar. This is less than or equal to t1 to t2 dt, and here is a little bit more complicated, but it's not so different. Minus phi h tilde square plus you have this derivative term. The d mu, I guess d mu epsilon t. And something like this. Plus epsilon to 1 over 8 or something. It doesn't matter so much. Okay, so this is a localized version of what we had before there. Okay. So I didn't derive this, but so the idea is similar. You just do everything, there you did it for phi equal to 1, basically. And here is you just, do a localized version with phi. We have pretty much all the tool you need, okay, to do this. Again, remember that the Lipschitz deformation part only reduces this integral, okay? So that's why you can insert this, you can replace it, yeah? That's right. Yeah. Okay, that's right. You could, change it. Actually, in fact, in my paper, yes, you do have to have also time-dependent case. Yeah. But that one's not so difficult to do. You just interpolate. So you kind of look at the time-discrete version of that, and then you end up having the time derivative term from the test function. Yeah. Thanks. That's good. Yeah. Yes, yeah, this doesn't depend on time, that's true, yeah. But since, this is true for each step, you can kind of look at the time difference also. Okay, and also maybe I should say that the volume change formula is also can be proved, so maybe just say that too, dx minus, t1. Yeah, this phi is actually doesn't have to be phi. Any C1 function is equal to I think this part was T, yeah, that's fine. This can be also proved, yeah, plus error. Okay, so that's a construction. And then after this, there's a lot of work to do still, unfortunately. But so the next thing is to prove that these guys, as j goes to infinity, converges to the Brakke flow. Okay, so that's still you have that step because this is discretely defined flow. So then you let j goes to infinity. Okay, so saying that this part is also sort of hard work, and well, before you do that, in fact, by using by using 25 and some argument, by using this kind of estimate, and by using 25 and also the argument that we had before about, remember we had this argument about compactness property of Brakke flow, the fact that we could choose one subsequence such that for all time, things the measure converges. You have exactly the same kind of argument actually here. And by using 25 and also sort of, okay, maybe I just say that. By using that and sort of a monotone, sort of semi decreasing property. With respect to time, we may we may choose a subsequence of jk or whatever, such that this measure, let's see, mu epsilon, well, now we have this j. Okay, well, I think, let's see, maybe there's a better. Yeah, okay, maybe I just say that the Hn of this gamma jk of t converges to a measure, okay, mu t, for all time. Okay, this can be done. Exactly the same kind of proof, because this property, this 25, really telling you that you have this extra term, but you can absorb this term to this one, and then you can actually show that this is sort of semi-decreasing property with respect to time. So again, using the similar idea, you can show that there exists a subsequence such that this guy converges for some Radon measure for all time. Okay, I mean, I might not explain so much, but that's sort of the idea. And so the hard part is to prove that this is a good measure. Okay, so for the moment, we have no idea. This could be any Radon measure, just by this abstract theory. Radon measure is always compact whenever you have bound. So this is, we don't know anything about it. But what you can prove is that this mu t is for almost all time. It's actually k integral. That is, it is supported on a k-dimensional set and integer multiplicity. Okay? So this part is kind of hard, actually, I must say. But so maybe remaining few minutes, I just say some little idea about this. Now, because of this estimate, okay, so because of this, what we have is that we have this kind of estimate of this type. So, this is h tilde epsilon gamma j t square, and let's see, 1 plus minus, okay, here it doesn't matter so much, but delta j, okay, so now here it's a j, and let's see, so Okay. Yep. Okay. And minus of delta J. Okay. Well, okay. Doesn't matter. Okay. Yeah, from the 24, yeah, you can just let T1 to be 0 and T2 to be capital T. You have this type of bound. Okay. And note that this is, okay, so maybe I put plus and then maybe the absolute value here. So this bound we have, independent of J, okay? And so, well, by Fatou theorem, for almost all time, this quantity is bounded, lim inf of this quantity is bounded, okay, by Fatou. Okay, so by Fatou, lim inf J of this quantity this quantity is bounded for almost all time. Okay. Yeah. And so you remember the following. You know, I explained this like second lecture maybe. You remember that this Allah's compactness theorem of integral varifold. Okay. So remember that what I explained to you was that when you have a mean curvature square integral bounded, then actually there's this compactness about this, you know, K integral measure. Yeah? So note that if you have this guy, if this is real mean curvature vector, okay? So if this is a real mean curvature vector, then Allard compactness theorem tells that the limit in T is actually K integral. Okay, I hope that the first part is fine. Yeah. So you know, this is not real mean curvature vector, but it's an approximate mean curvature. But if it is real mean curvature vector, then we have this Allard regularity theorem. Now, but we don't. You know, this is some sort of diffused version of the mean curvature vector. Okay, this is like a Gaussian diffused object. So you know, you don't have the information of this measure in a length scale smaller than epsilon, basically. Okay? But now this helps a lot because note that this is a quantity that tells you how much you can reduce by Lipschitz map, but you're dividing by this extremely small number. Okay, so having this bounded means, you see, this number is extremely small. Okay, delta Tj is, as I said, epsilon j to the 3n plus 20 or something like that. Yeah? So it's extremely small number, but dividing by this still is bounded means that this has to be small. Okay, so this means that you're really almost minimizing. You see, this is the amount that you can reduce by Lipschitz map. But this is saying that you can't do it. You can't reduce the measure. Okay? So you take advantage of this part to take care of the small length scale somehow. That is, you say that you cannot reduce the measure almost at all, meaning that in a small scale, it has to be like, by the way, so this Lipschitz map is the one that you're allowed to move only by 1 over j square. Okay, so that's another small scale, but your Lipschitz map is allowed to move only 1 over j square. So it's not like you can globally change the object, but you can only change only small scale. But the thing is, you cannot, reduce a measure very, very tiny amount. You're allowed to reduce a measure. So in a small scale, you can even actually prove that if you sort of blow up by a scale of 1 over j square, if blown up in a scale of 1 over j square, then actually you can actually show that this small scale is actually area minimizing. Okay, because this is extremely small. You cannot reduce the measure by this Lipschitz map. So in a very small scale, you can show it's actually area minimizing, which gives you a good regularity. Okay? So it's the scale 1 over j square, you have almost area minimizing, and you have this control in a larger scale, and combine these two things, actually you can prove the similar end. That is, you can prove that it's actually K integral. So this part takes a lot of effort, actually, because not only that, but you really have to take advantage of this part. So, and in some way, it's an extremely harder version of like Allen-Kahn singular perturbation limit problem, actually, because for Allen-Kahn equation, you also have this epsilon scale where you know things looks good. So in a way, it's very similar. It's sort of hidden in this is a somehow similar idea. And yeah, so this part tells you this K integral part, and then again, also you have to prove the limit is a Brakke flow, and also you have some other things you have to prove, but yeah, some of the main things I think I at least gave the idea of how the proof goes. Okay, so I think it's about good time, and thank you very much for your attention. All right. Thank you.